Vector fields. Welcome to the new chapter of your final calculus course. And I was thinking how to politely tell you it's going to be the hardest one. And then look at that, Dr. Payan figured out, he says, like a boss at the battle in the computer game, this chapter is unbelievably hard, but also unbelievably exciting. Right? Impressive, right?
No.
It's like a boss of your computer game. So, a last boss of the computer game.
Well, I am the boss of the computer game.
So, a vector field. Let's figure out what a vector field is. Is a function. Are you guys done? Any questions? Is a function that associates each point with a vector. So basically, vector field is a bunch of vectors. How simple is that? And you saw it before, you just don't know it. So please write down this definition. This is a vector field on R2. That R2, do you know how to draw it? Like so. R with a line in front of it. That is 2D, right? Vector field in 2D is a vector function. But then the function f has pi p. P times I and q times I, which assigns each point. This one is in 2D, so we could do 3D as well. Why not? We're going to have some 3D examples too. The vector f. So for each point, we're going to have a vector. For each point, we're going to have a vector. And that's going to be infinitely many vectors with different directions. So a vector field f is a function that associates to each point x, comma, y, a vector f at x, comma, y, with a corresponding rule, and that rule will be the hardest part. The rule will be different from function to function, as always. So, examples in the real life, of course, wind maps are amazing. You saw this before, and the thing is, remember I told you when you drop a ball, it's interesting when it's gonna go. With the wind, if you drop a paper plane, where it's gonna flow. So that is interesting. This is how exactly they figure out, and they color code it. You see, with the how strong the wind is, with red and yellow. Yes.
Sorry, go up for like a second.
Oh, I see. So winds, electromagnetic fields, gravitational forces, black holes. We're gonna talk about these things. Explosions, not anymore. But maybe the explosion of the supernova that also have lots of gravitational forces happening. So that's gonna be interesting.
Excuse me. What's the R cube?
P and Q? Yeah. P and Q.
No, it's the R cubed. It's a vector in 3D space.
Oh.
Yeah. So R, this is 2D. That's notation of 2D.
And that's just
And this notation of 3D.
3D. Okay.
Yeah. It's a real numbers, and square means double second dimension, 3, third dimension, 4, fourth dimension.
What does the fourth dimension one look like?
But we're working with it all the time. 3 dimension is your body. Fourth dimension, for example, density of your body. The bones are firm, but the skin or liver, they have liquids inside and stuff. So fourth dimension is some kind of force quality that is changing across your body. Or temperature, or time. You're getting old right now while you're breathing.
No, I refuse.
Ocean currents, look at that, super pretty as well. Very nice to see if your home in Florida will be flooded this time or not. And now I will show you some cool animations. Of course, this class requires lots of cool animations. I've showed this in my Calculus 1 and 2 classes, and I said we're going to learn this in Calculus 3. It's going to be hard but fascinating. So let's see. That is not an animation after all. Okay. Yesterday I found lots of cool animation. Okay, here it is. So they either represent with balls or with wind, kind of like moving object. But again, imagine you're dropping a ball, and to know where it's gonna go, you use vector fields, which can be magnetical fields or winds or water flows and so on. So your job will be to understand mathematically how to show this. This one is spinning one, and you see the one that spins faster is not the same as the one that spins slower. You need to learn and detect those spinning locations, which are like water flow, what's the name? Anyway, some water, some collection of water, for example, and so on, from the vector fields maps. This one is pretty cool. This one looks like magnetic field. Then let's see what else is here. This one is color coded in 3D, so we have to learn how to build this in 3D as well.
Do we have to draw it?
The lines here are already drawn for you, but actually not supposed to. You're supposed to figure out the lines yourself.
If we draw it,
Right? This one I showed you before. This one is like easy representation in 2D. How do you know where something is going? So with people, as you can see, vector field tells them to go to the left, to the right, or straight. And different speed. You should also see different speeds here. And the last one is not working. Okay, never mind. So let's illustrate. Here's an example. Write it down. We can illustrate a vector field by plotting at each point a vector with its tail at xy. Write down this phrase. It's actually a really nice explanation of what is happening. We can illustrate a vector field by plotting at each point a vector with its tail at that point. That is a confusing part, so I wanted to have it as a nice explanation.
At xy?
xy.
Why is the tail? Should it be the head?
Yeah, you will see, and that's a new thing here, so we will have to get used to it slowly. It will a little bit contradict of what we did before. So example, the easy one is when x and y match x and y. Vector field F at the point, this is the point, x comma y, gives you a rule, and the rule for now is the most easy one, x comma y. That is rare when we have such a good rule, but it is vector notation, as you can see. So let's see what is happening here. So what is F at 1, 1? That's it. This is a point, 1, 1. It gives you a vector 1, 1, which will draw. We will have to find a point 1, 1, and then from this we'll have to figure out the vector 1, 1. So it starts from the point. That's interesting. It starts from the point pointing to 1, 1. Do you remember how to draw vectors? It was the first week of class. 1 to the right and then 1 up, right? So 1, 1. Drawing vectors, we're going to do it a lot right now. How about 3, something random? 3 and 1 is a vector 3 and 1. Vector means in 2D 3 unit strengths into x-axis and 1 unit strength up. So it will be more tilted now, like so, if you remember. But it starts at the point 3 and 1. And so on. You can plug whatever you want. In this case, they just match. This is very rare coincidence. At 2, 2 it is 2, 2 at minus 3 and 1. It will be minus 3 and 1. How to draw all of this? It's basically the perfect match of the point to its location and direction. Again, you find the point 1, 1 and its tail, now you start a vector 1, 1. You find a point 3, 1. You find a point 2, 2. And now, whatever the point is, that's going to be the length of the vector. So if it's 2, 2, then this side is 2 and this side is 2, which gives you interesting understanding. The farther away from the 0 you go, the longer each vector is going to be. If this is 100, 100, then the vector will be, right, super big, 100, 100. So that's interesting to understand. And vice versa, the closer you are to the 0, maybe like 0.1 and 0.1, the smaller this vector is going to be. So this is how it looks like. It looks like arrows shooting away from the center. And the farther you go away, the bigger they become, the vectors. Yes?
Can you have more than one vector from the same point?
Good question.
It's an interesting question. No, we're going to have, let's see.
What about the origin? The origin have like, ooh.
0, 0. At origin, it will be 0, 0, so it will be just here. You are talking about not 1-to-1 cases. This case is 1-to-1. 1 point is attached to one vector. That's a very smart question. So she's asking if it's possible at one point to have this vector and this vector at the same time. I think in this class we only cover 1-to-1 cases. So not supposed to. In this class, not supposed to. I will check if I remember I was doing something like this in upper level classes. So I will Google for you until next time. That's a good question. For now, she is right. Like we always have exactly one number, 10 and a million to one vector. How about we have one input but 2 outputs? So that's interesting. So as you can see, now you can have some intuition. Oh, the farther away you go from the center, the stronger the wind takes you away, right? Any direction you go, even if it's negative 100, negative 100, the vector from this point will be huge and go into negative directions. So that's kind of intuitional idea here, and that's called a vector field. A vector field. That was a way too easy example, so we need to do more. Many applications: force field, velocity field, gravitational field, electrostatic field, emotional attraction. I guess so.
But of course.
Let's do something more unusual. This will definitely crack your mind a little bit. F of x comma y, not only it will be y coordinate first, but it's also negative y. And then x is the second one. And now it will be a little bit hard for the brain to figure out, so which place goes where. Let's see. F at 1, 0. What is going to be? 0 minus my... So 0...
1.
Yeah, I know the answer. my point is how to explain it. So this is x. So this will be 1. This is y. So you should keep making note about this. Now, how about 0, 1? What do you think about that? Minus 1, 0. So
Good job.
good job, people. Good job, Julia. Good job to myself. It's minus 1 goes to the right, 0 to the left. F at 0 minus 1 though becomes 1, 0, because minus gives you 1. So carefully plug it in. The first coordinate goes to the second one goes to the first with a negative sign. That is unusual. Now it's a little bit different idea here. First of all, you should kind of imagine what is happening. So imagine this is like a huge magnetic field or a wind field. It's infinitely big, because at infinity you can see it goes to infinity. When x is very, very big, and x in 2D right now goes to the left and right. We only work in 2D for now. When x is huge, the y coordinate becomes huge. Isn't it interesting? So the farther away I'm going to the right or to the left, actually a vector becomes very vertical, up or down, right? When y is huge, then y is going up and down. The farther away I'm flying away from bottom to top, the more negative the first component of the vector becomes, which is x. And negative means the opposite direction. So let's see what it means, and then try to guess what kind of field it is going to be. So when I mention the first point, 1, 0, 1, 0 is over here. That is the point. At this point, I need to plot a vector 0, 1. 0 change in x-axis, because this is x component. That's what I'm trying to explain. This is your x component, and this is your y component. X component tells you 0, so no change in x, but y goes up to 1. That is the vector called 0, 1. It's perpendicular to x-axis, as you can see. Yes?
So the way we calculate the vector is different, but it's still x component, y component.
Yes, exactly. So it's not convenient to call them x and y. It would be nice to call them mj, tm, so don't get confused. But it's true. The first component is still x-axis. Run. The second component, rise. And if there's a third one, depth, z. Now one more point. So we calculated point 0, 1. It's over here. 0, 1. 0, 1 says, well, now we change x-axis in the opposite direction of you wanted to go. You wanted to go to 1? No, we're going to minus 1. That is like so. And there's no change in y, so it's minus 1, 0. The farther away I'm going, so from this point, it will go like so. From this point, it will go like so, all size 1. However, the farther away I'm going from the center, for example, if I do somewhere over here, this is the point, I don't know, let's make up something like 3 minus 3. This is the point. what kind of vector it should be? 3 minus 3. The vector we should build now will be what? 3 and 3. So not only it goes to the positive direction of y, but also to the positive direction of x with a size bigger than 1. It's 3 square plus square root. So it becomes bigger when we go away. Then the same thing will happen with this one. The same thing it will happen with this one. It goes the opposite direction because of y. And the same thing will happen from this one. So it looks like some spinning rotation, and the farther we go, the bigger it gets. So it will be even bigger over here, and so on. Pretty cool idea. Yes?
Is there a reason that we're changing the initial values of the vector?
No, I just randomly plug some stuff.
No. I'm saying the fact that we're changing it to negative y comma x. Is there like some sort of intuitive?
Yeah, you can do some. There is actually a very good question. Intuitively, that's how you build perpendicularity of the problem. So that's very nice. Shh! You guys are talking too much today. I usually do 3 warnings in class and then I kick people up. So warning number 1 is perpendicular to x and y. So very interesting that the field itself is perpendicular to every vector over here, because if you have a vector x comma y multiplied by x comma y, so vector field multiplied by x comma y, you now can plug in. The first one is actually minus y comma x. Minus y comma x is multiplied by x comma y. This is a dot product. If you don't remember what dot product is a scalar product. Scalar product will be minus y times x plus x times y equals to 0. So this is the explanation. Because the dot product is 0 between the f and the vector x comma y. And that's why you build perpendicularity with this one negative sign and reversing the order of inputs. So you can build and force the vector field to be perpendicular this way, or you can describe the perpendicular forces, magnetic fields and stuff, with the negative sign and switching the order. That's a pretty cool idea here. And it looks like so, if you want to know the graph. Here is the vector x comma y. And then from here, you build a perpendicular angle, a right angle, f at x comma y will be perpendicular to it. And we can always write it down like so. F x comma y equals, which was minus y and x, is minus yi plus xj. And this is the first formula that we wrote today. It was p and q, if you remember at the beginning. So that is what's happening. The first component and the second component. Where you remember, can you tell me what is I?
I is the first component of a vector.
0, 1.
Yeah, I meant 1, 0. You both are very close to the correct answer. But J is 0, 1. Julia, not Jacob. Minus 5 points on the final exam.
Exactly. Your name's not even Julia.
So this will take a while to get used to as well. And then we will give you, well, we'll still have 10 minutes, so I can show you one more example. Questions about this one? What do you think for now about this? Yeah, it is going to be not easy. Yes?
So when it's perpendicular like that, is that kind of similar to when we did the gradient?
Similar to what?
When we did gradients?
Oh yeah, we're gonna mention gradients literally right now.
Oh, okay.
So I will explain it on Monday, but you have very good questions because exactly that's what we're gonna. So this is the pretty version of this graph for you to know, but it's exactly what we're gonna mention is the gradient vector field. But before going to that, I wanted to show you this example. It's actually pretty cool. It's not example number 5. I think it's number 3, and it looks kind of crazy, but it's actually very simple. But it also illustrates how you have to get used to scary notations. Well, you kind of did already. What else can be scarier than triple integrals, right?
Quadruple integrals? This.
The answer is correct, this, because it's getting scarier after this. So this is a nice example. I think it's number 3. Write it down, and I have more questions. Yes?
Is this something that we should be writing down, or is it just something that's like?
This one you should write down. Yeah. Yeah. I'll give you all the notes, so it's fine. Here's the example. Sketch the following vector field. So simple. Minus x over square root of x squared plus y squared. That's the first component. Minus y over square root of x squared plus y squared. And you're like, wow, this looks not good. But, again, we can write it down as rewrite. And people are like, wait, we did not write the first one yet. Rewrite f x comma y. It's nice to rewrite it just with standing x and y in front. That's where the dot product comes in, or the, well, it's not the dot product actually. Here you can just take these components out, kick out this x and y outside. Then the common part which you're factoring out minus 1 over a square root of x squared plus y squared. So you factor out this common piece. And the first thing that the scientist notices is this negative part. Negative part, like we just agreed, says something will be happening the opposite direction of the point. Every time you choose x and y, you have to point to minus x and y. So you chose the location 5, 7, point to minus something, because negative creates everything the opposite direction. So we will have, so it points, let's do it. It points the opposite direction from the vector x and y. Let's check it out. So first of all, we figure out this part. When you have a vector x comma y, you will have to reverse the direction for f at x comma y. But what kind of size it will have? You see, so I do some random size of it. I don't know how big or large it is. Maybe it's even bigger. But for now, we know it's going to be the opposite direction because of the negative sign. Then you can figure out the size, the magnitude, right? What is the vector again? What's the definition of the vector? Who remembers? Direction and magnitude, right? It has direction and magnitude. Let's find the size of f, which is the magnitude. How do we find the size? We will have a huge square root and square each component. Each component are those crazy minus x over a square root and minus y over a square root equals. Okay, let me write down. What is the square root? X squared plus y squared. X squared plus y squared. When you square, it gets rid of the negative sign. It gets rid of the square root, but only inside square roots. Outside square root stays. And you will have x squared plus y squared at the top. And conveniently, common denominator x squared plus y squared at the bottom. Yes. So the answer is 1, which means the size of each vector is just 1. Now we just need to figure out, so let me write down and I will answer. F of x comma y has length 1 no matter where the location is. So that's a unit, it's a vector field full of units vectors, yes. What was the question?
Why isn't it plus minus 1?
Oh, not plus. You just cancel it out. So it's the square root of 1, which is 1.
Plus minus 1.
No.
Okay.
Yeah.
No.
Professor,
Yeah.
scroll a little so I can see the opposite.
Yeah. So then now let's think about that. When I'm choosing the point 1, 1, it will go away to minus 1, or whatever it is, with the size 1. When I choose 2, 2, it will go away to minus. If I choose 5, 5, and the length will be the same. So it will look like so. Very interesting idea. It will look like a very nice magnetic field example. For example, a black hole. or any magnet at the center, they all have unit vectors, so we don't care how strong it is. Seems like it have the same strengths no matter where you're located, but you are getting dragged to the middle. So you choose any location, it still goes the opposite direction. So you chose 5, 5, it goes with the strength 1 to minus, minus. Only at 0 it stays 0, 0, so the closer you are to 0, the closer you are to 0. That was not a very smart conclusion.
So why does black hole have gravitational pull?
What? Oh yes, we will actually talk about this. There's part of the book that talks about magnetic fields. I usually don't go deeper into that, but people who are professional magnetic fields, they do. Yes.
Are we able to switch to like polar coordinates since we have an x squared plus y squared?
We will talk about it later, but I do know why you keep saying that, because every time you see x squared plus y squared, we taught you it's nice to switch to polar. In this case, we don't even talk about different coordinates anymore for now. Soon I will explain you that we can use different ones, but for the vector fields, for now even this is hard. But we did not even go to 3D yet. So in 3D, like I showed you here, oh, I can show you here. In 3D it will be even harder to draw, because it will be, oh. That is a nice theorem we need to, yeah, we're gonna talk about that. That's a nice theorem here. But I'm probably just gonna show you this again. In 3D, it will be something like this. So, since those are still vectors and they're flat, they're still flat objects, even though they define through square roots and stuff, we use Cartesian most of the time. But we're gonna go further into this later. Good questions, people. Good job.
Yeah.